All right, so the next thing that we're going to do is talk about a fourth method for approximating the area underneath the curve, and that is called the trapezoidal rule. And you'll note that I've got this different notation up here, right? With this like little squiggly line. That little squiggly line is what we call an integral sign. We're going to talk a lot more about that later. But for right now, just read this right here as the area underneath f of x from A to B. So from A to B, what's the area underneath that curve? That's what that means. Okay. So hopefully you remember from a couple of weeks ago before break, one thing we were doing was we were looking at left approximations, right? We made the left endpoint, we made a rectangle, we went to the next left endpoint, we made a rectangle, we went to the next left endpoint, and so on. We made some rectangles that way. You all remember doing the area of each rectangle, and we added them together, and we said, oh, that's about the area underneath the curve. That sound familiar?
Yes.
Oh, good. Okay. And we also did it with the right side, the right endpoint. Right? We made some nice little rectangles here that looked like this and figured out those areas. Yeah? Remember doing that?
Yeah.
Okay. Cool. And we also did some with midpoints. So like we found the midpoint of the interval and made a rectangle there. And the midpoint of this rectangle and made it. So our midpoint of the interval and made the rectangles. Right? Everybody remember that?
Yeah.
Yep.
Cool. All right. Those were the three things that we did on that last day before vacation, I think. So today we're going to talk about the fourth method, which is the trapezoidal rule. So rather than making a bunch of rectangles, we're going to use trapezoids. Now you're all familiar with trapezoids, right? Trapezoids have two parallel bases, right? And then the ends of those little line segments are connected, right? It could look like that, or something like this is a trapezoid, right? These don't have to be the same. They don't have to be anywhere close to at the same angle. Those are trapezoids, right? We all remember what a trapezoid looks like, the parallel bases and all that crap. Good. What's the area of a trapezoid? You should know the formula for the area of a trapezoid. That's something you should know. This is
Like times average of the bases.
All right, the height times the average of the bases. Base 1 plus base 2 divided by 2 times the height. That is the area of a trapezoid formula. You should know that. So we're going to use that to develop an approximation for the area under the curve. So first thing I'm going to do is I'm going to draw my trapezoids. The way I draw the trapezoids is I take the first endpoint of my interval, and I just draw a straight line going down to my function or up to my function, depending on if I'm above or below the x-axis. And I do the same thing at this one. Those are the bases of my trapezoid. They're parallel to each other. Those are the two parallel sides of the trapezoid. Connect those, which will always just be perfectly horizontal. And then connect those using a straight line. Okay, so there's my first trapezoid. And then I'm going to do the same thing with this one. I'm going to go down to here, connect those, and draw a straight vertical line down there too. Everybody good with that? We're just going to keep doing this over and over again. This one's a little weird because we cross through the x-axis, so really this one just becomes two triangles, but that's not a big deal. Same thing here, and here, and here, and there. Good or no? Everybody sees all the trapezoids in there?
Yeah.
Wonderful. Okay. So what is the area of the first trapezoid? How do I find the area of this first trapezoid? I need the first base and the other base, right? I need the two bases. How do I find those values?
Isn't it like you take f of x sub 0 and then f of x sub 1 to find the bases?
F of x sub 0 and f of x sub 1. So I'll just call those y sub 0 and y sub 1. Rather than f of x sub 0, y sub 0 is good enough. And then we need to find the average of those, so divide it by 2 and multiply it by this height. Right, this is the height of the trapezoid. And then to do the next one, we would need to find this base and divide by 2 and multiply by the height. And so on and so on and so on until we've done all of the trapezoids. Everybody agree with that?
Yes.
Cool. So that's where this formula comes from. Each individual height times base 1 plus base 2 over 2. Then the next height, base 1 plus base 2 over 2. And the next height, base 1 plus base 2 over 2, all the way till I get to the end. And now, there are two different situations that we could be in. The first is that each of these subintervals might be of different length, right? So this height might be 1, and this height might be 2, and this height might be 1.5, and so on. All the heights might be different, right? Or some of them might be the same, but others might be different. If that's the case, if you have different heights, you have to find the area of each trapezoid separately, and then add them all together. And it's kind of a pain. Okay? But what we can usually make happen is we can usually make it so that each of these subintervals are the same length. And if each of the subintervals is the same length, what can you tell me about the height of each of the trapezoids?
They're all the same.
Yeah, the height should all be the same. And so if h is always the same value, I should be able to factor an h out of this. And if I'm dividing them all by 2, I should be able to factor an h over 2 out of all of them, shouldn't I? Would you all agree that I could take an h out of 2 out of each of these terms between the pluses here?
Yes.
Yes.
All right, and what's left? Y naught, or y sub 0, right? Plus another one here, y sub 1, plus another y sub 1, and then plus a y sub 2. And I know a bunch of dots in here, but here's y0, here's y1, here's my y2. What do I add to the next one? The next one should be a y sub 2 and a y sub 3. Right? And the next one should be a y sub 3 and a y sub 4, and so on. Until I get to the end, and I'm going to have 2 of the y sub n minus 1s, but only 1 of the y sub n at the end. True?
Yep.
Good. So we'll note that only y naught and y sub n, the endpoint intervals, only get used once, but all the other ones get used twice, right? True? So we should be able to rewrite this as this trapezoidal approximation, which we'll just call capital T, is h over 2 times the first y value plus 2 times the second y value plus 2 times the third y value, and so on and so on and so on, all the way until we get to just 1 of the last y value. Everybody agree with that? Everybody good with that?
Yes.
Okay. Now, the only thing that's left is to figure out what is h. And so if we think back, what is h? The height of each of these ought to be the entire length of this interval divided by the number of subintervals that we have. Would you guys agree with that? the height of each one should be the total length divided by how many there are?
Yes.
Yeah. So the total length is b minus a, and n is the number of subintervals. So h will always equal b minus a over n. Good or no?
Good.
All right. And so one other important thing to note is that this is the same as finding the average of a right and left endpoint rectangular approximation. So it'll come out to be exactly the same if you do either one of those, trapezoidal, or you do the right and left and average them. But often it's easier to get the trapezoidal approximation if you have equal subintervals, because you can just use the formula. And it's going to be a better approximation than any of the other approximations are as well. Everybody good? Any questions? All right, so what we want to do is we're going to use the trapezoidal rule with n equals 4. So that means 4 subintervals. And we're going to look for the area under x squared from x equals 1 to x equals 2. That's what we want to try to find. Do you think we could find that? Yes, no, maybe, maybe not, definitely.
Yeah, probably.
Probably. Gosh, I hope so. Okay. So let's do that. Our interval is from 1 to 2, and we have 4 subintervals. So the first subinterval will be from 1 to 1 1/4, and the next will be from 1 1/4 to 1 1/2, and then from 1 1/2 to 1 3/4, and from 1 3/4 to 2. So there's 1, 2, 3, 4 subintervals. Everybody good with that?
Yep.
Wonderful. Okay. So then let's put it into our formula. What's b minus a? That's our h, right? b minus a over n. That's h. Should all be divided by 2 based on our formula, h over 2, where h is equal to b minus a over n. So b minus a, we're going from 1 to 2, so 2 minus 1, over n, 4, divided by 2. Everybody good with the b minus a over n over 2 part? Yes, no, maybe.
Good.
Okay. And then what should our y sub 0 or y not be? Should be this x value squared, because our function is x squared. If it was x cubed, it would be that x value cubed. If it was x plus 1, it'd be that x value plus 1, right? So this should be 1 squared. And then the next one, which is y sub 1, we should have 2 of those, right? So 2 times 5/4 squared. And we should have 2 of the next one, 2 times 3/2 squared. We should have 2 of the next one, 2 times 7/4 squared. And then the last one, we should just have 1 of, 1, 2 squared. Good or no?
Good.
b minus a over n, 1/4 over 2 is an 8. And we got 1 plus 25/16 times 2, or 25/8. 9/4 times 2, or 9/2. 49/16 times 2, or 49/8. And 4. And what does that simplify out to become? Anybody?
(75/32).
Ah, good. That's what I got. Any questions or issues on that?
Going back, what does that symbol really mean? Where it's just to estimate, like, is that like an f sub 1 squared x squared d of x thing?
I'm not sure what you're asking. Which one? What are you asking about?
In the question where it says use the trapezoidal rule with n equals 4 to
Oh,
estimate.
this just is
Yeah.
saying that what that is technically is an integral sign, which we're going to talk about in a minute.
Oh,
But it
okay.
just means find the area underneath this curve from 1 to 2.
Okay.
Yeah, in a little while, we're going to, and pretty soon, by the end of today, we're going to be using that symbol for everything.
Yeah.
So, yeah, that just means find the area under the curve. Good?
Good.
Okay. Anybody else, any other questions before we move on? All right. Now, next thing is sigma notation. Are you all familiar with sigma notation?
I've seen it before.
And are you 100% comfortable with it and know exactly what it means and how to deal with it?
Not 100%, no.
And my guess is that that's the majority of you. Is that true? Most of you have no idea how to do sigma notation?
Yeah, I'm kind of like 0%.
Yeah.
Okay, that's what I figured. That's how first period was, or fourth period, or whatever period it is. So sigma notation, this is a sigma right here. That's a capital sigma. It just means sum together, add together a bunch of stuff. So that's what we're going to try to do here. We're just going to add together a bunch of things. And in this case, it's saying sum together all of the a sub k's from the first one to the nth one. And so effectively what that means is, it means take a sub k and list out all of those from k equals 1 up to k equals n and just add them all together. So that's what I've done. I've said a sub 1 plus a sub 2 plus a sub 3 plus dot, 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 all the way up to a sub n. Good or no? Yes, no, maybe?
Yeah.
All right. So if I said sum together from k equals 1 to 3, all of the a sub k's, that should just look like a sub 1 plus a sub 2 plus a sub 3. Good or no?
Are you always just like, oh, never mind, sorry.
All right. Now, what if I said, is that everybody okay with that? Just that little part?
Yeah, good.
Okay. So what if instead of having a sub k, I had a sum from k equals 1 to 4 of k? What would that mean? What do you think that would mean?
Would it be like 1 plus 2 plus 3 plus 4?
That's exactly what it would be. It'd be k equals 1, so 1. And then the next one would be 2. The next integer would be 3. And the next one would be 4. And now that I've got to the fourth one, I stop. Easy enough?
Yeah.
Okay, good. So if I asked you then, let's say, well, let's say I asked you, what was the sum from k equals 1 to 3 of k squared? What would that mean?
Be 1 squared plus 2 squared plus 3 squared.
Exactly. And if I asked you, what was the sum from k equals 1 to 4 of 5? What would that be?
Would it just be like 5 plus 5 plus 5 plus 5?
Yep, I would add together 5s from the first 5 to the fourth 5. It'd just be 5 plus 5 plus 5 plus 5. What if I asked you to sum together from k equals 1 to 4 of 2k? What would that be?
Would it be like 2 plus 4 plus 6 plus 8?
Yep, it'd be 2 times the first k, and then 2 times the next k, and 2 times the next k, and 2 times the next k, which would just be 2 plus 4 plus 6 plus 8. These all have a multiplication by 2 in common, right? Wouldn't that be the same thing?
Yes.
Yeah, and so we could then note that if we had a constant inside of this summation, 2k, we could pull that 2 out to the front of it. If it was a 3k, I could pull a 3 out. If it was a 1/2 k, I could pull a 1/2 out. Sort of an important thing that we should know about summations.
What if you had like a decimal or a fraction on the top?
You will not. Yeah, these are only integer values that we'll have in here, or natural number values, in fact. They'll only be positive integers.
Oh, okay, that makes sense. Thank you.
Let's see. What if I said the sum from k equals 1 to 3 of 3k squared plus k plus 1? What would that be? First term would be 3 times 1 squared plus 1, right? And I would add to that 3 times 2 squared plus 2 plus 1. And I would add to that 3 times 3 squared plus 3 plus 1. True? Everyone would be okay with that? K is 1 in the first one, K is 2 in the second one, K is 3 in the third one.
Yep.
Would that be the same as doing these separately, summing 3k squareds from 1 to 3, and then summing k's from 1 to 3, and then summing 1s from 1 to 3?
Yes.
Yeah, it should be the same, right? I have the 3k squared part is from 1 to 2 to 3. And then I've got the k part from 1 to 2 to 3. And then I've got just the 1, 2, 3 times. So we could do the summation separately if we wanted to. We could pull out constants. We should be able to sum together a constant, or we should be able to sum together any variable. That's kind of the very basics of summations. Does that all make sense to everybody? Anybody have any questions on that?
Is there like a name for the little like E thingy?
Yeah, that's a sigma. It's a
Okay.
capital sigma. It's just a Greek letter. Good or no? Any questions? All right. Let's make it a little bit more complicated. All right, you have, let's see. Let me put up a problem here. All right, you have 20 seconds to solve this and tell me the exact numerical value of this.
Is it 50-50?
Yes. Anybody else get that? You have 3 seconds
Yeah.
left
I got that too.
without using your calculator.
Yep.
Ah, good. All right. So you know how this works already, yeah?
Yeah.
That's good news.
Maybe. I don't know.
All right. So, see, during fourth period, nobody was able to do it fast enough. What is the sum from k equals 1 to 100 of k? Well, it's 1 plus 2 plus 3 all the way up to 100, right? That's what that means, isn't it? True? Yeah,
True.
that's what that means. So we could also write it backwards. Because you can add in any order, right? Addition is commutative, true? You can add them in any order. And if I have two things that I know to be true, I can add them both together. This would give me 2 of these. And this would be, let's see, if I added 1 plus 100, that'd be 101. And what if I added 2 plus 99? What would that be?
101.
And 3 plus 98? Still 101. And all of them in between would be 101. And 99 and 2 and 101. Right? 101 would make 101. Good? Well, so what does 2 of these summations equals? Well, it's 101. How many 101s do I have?
$100.
I have 100 of them. And so to figure out what the actual summation is, I just take 101 times 100 and divide it by 2. And that comes out to be 5,050, right? Which is super cool. You may not think it's that cool, but we could use this same exact concept to come up with a generic formula to sum together the first however many integers we wanted, or natural numbers that we wanted. Right, if I wanted to sum together the first 733 integers, we could use this same process. And so what we're going to do real quickly is we're going to say, what if this was the sum from k equals 1 to n of k? And that'd be 1 plus 2 plus 3 all the way up to the number before n, and then n. Everybody agree that that's what that should be?
Yeah.
Okay.
That should be.
And it could also be rewritten backwards. So n plus the number before n plus the number before that. And when I bring them together, add them together, we'd end up with two of these summations should be, well, 1 plus n is just n plus 1. And 2 plus n minus 1 is another n plus 1. And another n plus 1. And how many n plus 1s do I end up with in the end? How many n plus 1s do I get?
And
I should have n of them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, n. So 2 times the sum from k equals 1 to n of k should be equal to n plus 1s. Or just the sum from k equals 1 to n of k. So the sum of all the natural numbers from 1 to wherever we want is always equal to the number that we want of them times the next number divided by 2. And my assumption is those of you that came up with 5,050 really quick, either plugged it into a summation on your calculator or you use that formula. True?
True.
Yes.
So this only applies to k equals 1, right?
This only applies from k equals 1. Yeah, that's true. But if I wanted to do it from k equals, if I wanted to go from add the numbers from 10 to 100, well, I could just figure out what it is from 1 to 100 and then subtract what it is from 1 to 9. So I could just use the formula twice. Does that make sense?
Yeah, kind of.
Yeah, I mean, so like, well, I'll do that in a second. I just want to finish talking about this real quick. So this is an important formula that you want to know and memorize. If you want to sum together all of the natural numbers from 1 to anything, you just use this formula. Very important. You need to know that. So what I was going to say is if we wanted to find the sum from k equals, let's say 10 to 50 of the natural numbers, we could just say this is equal to the sum from k equals 1 to 50 minus the sum from k equals 1 to 9. Okay, that's what I was saying. Does that make sense?
Yeah, kind of.
Right, if I want to add the numbers from 10 to 50, add up all the numbers from 1 to 50, and then subtract the numbers from 1 to 9. So this would be 50 times 51 over 2 minus 9 times 10 over 2. So whatever that comes out to be, I don't know, but hopefully that makes sense. Next thing I want to real quickly talk about is we did this one a little bit ago, something like this. We said let's sum together from k equals 1 to 5 the k's. Not the k's. Let's sum together from k equals 1 to 5 the 7s. Right? This is just 7 plus 7 plus 7 plus 7 plus 7. Right? If I just have a number here, the first 7 is 7. The second 7 is 7. The third 7 is 7. The fourth 7 is 7. And the last 7 is 7. Right? So anytime we have a summation of just a constant, it's just that constant times however many of them we're summing together. Okay. So if we, and I'll write it this way, the sum from k equals 1 to n of a is equal to a times n. Does that make sense? So that's another thing you should just sort of know. Good or no?
Good.
Okay. And last one, which we're not going to prove, but if you want to, you can go online and look at it sometime and see the proof. If I wanted to sum from k equals 1 to n of k squared, so all of the squares, and this one comes up quite often, you should know the formula for this also. It's n times n plus 1 times 2n plus 1 all over 6. Okay. So memorize that formula as well. Good or no? Any questions?
Good.
All right, everyone's good, no questions? Cool. So let's start moving back to what we were doing with the areas under the curve, because we're going to use these ideas in just a minute. And what we're about to do is going to get fairly conceptual. I'm going to try to make it as basic as I possibly can, but it's going to seem pretty complicated still, is my guess. So just bear with me. If you have questions or you don't understand something I'm doing, please stop me and ask. So what I've got here, again, is I've got some curve, f of x, we'll call it, in blue, that I've drawn around the x-axis and the y-axis. And I put in some rectangles that I've used a midpoint rectangular approximation for. I didn't draw all of them. I drew the first couple, and then I drew some other rectangle in there, some arbitrary rectangle within. And so note that as I labeled them, I called the first point x sub 0, and then x sub 1, and then x sub 2 for each of these subintervals, and x sub 3. But somewhere along the line, I just called one k minus 1 and k with a midpoint of c sub k. So I picked some random subinterval within here, and I labeled it as a k for the kth subinterval. And so what have we been doing previously with each of these like area approximations? We found each area, right? And then what did we do with each of the areas?
You just add them all together, right?
Right, we just added them all together, right? That's what we did for the left ones. We did that for the right ones. We did that for the midpoints, and that's what we did with the trapezoidal, right? So we just found the area of each one, and we summed them all together. Well, doesn't that sort of sound like a summation? All these fun things we were doing. Yes? No? Maybe? We're
Yes.
summing together a bunch of areas. So perhaps if I wanted to find the area underneath this curve, we could say, let's sum together all of the areas of the rectangles. Right? We're going to sum together from the first area of a rectangle to the nth area of a rectangle. Okay. Good? That's what we want to try to do. Now we're going to try and get a shorthand notation for all of these adding togethers that we've done. And we have to do that using a summation. And so that's why I've labeled one of them as the kth subinterval, so that I can find a generic formula for the area of this rectangle that could be applied to any rectangle I wanted. And then I can put that area in terms of k into this formula, into this summation, and then use this idea of the summation that we've been talking about to find the value. Does that make sense? Without having to calculate each one separately and then add them together. Good or no?
Good.
Okay. So previously, when we did the left and the right and the midpoints and even the trapezoidals, we didn't have that many subintervals, right? We had like 4 subintervals or 3 subintervals or maybe up to like 8 subintervals or something crazy like that, right? But nothing too horrible where the amount of arithmetic that we had to do wasn't so bad. But we, I think, a couple weeks ago talked about what would be helpful to get a more accurate representation of that area. What would we want to have?
As many subintervals as possible?
Right, as many subintervals as possible. Like having 4 subintervals, not so great. Okay, gives us an okay approximation. The arithmetic's not bad at all. And if I have 10 subintervals, well, that's going to give me a better approximation, but it's going to make the arithmetic more irritating, right? What if I had 100 subintervals? Well, that's going to make my approximation really good, but it's going to make the arithmetic a giant pain, right? And if I want to have 1 million subintervals, well, I'm going to spend the next 5 years doing all the arithmetic, unless I can come up with a generic formula and put it into the summation and use some of these little tricks that we found that worked out real nicely to evaluate that summation very quickly. Does that make sense? Why we want to put it into the summation? Basically, the summation is going to allow us to have as many subintervals as we want without complicating the arithmetic. Good or no? Yes, no, maybe?
Good.
Good, okay. All right, so that's our goal. So let's write out a formula for the area of the rectangle in the kth subinterval. So that area it's a rectangle, so it should be length times width, or base times height, or whatever you want to call it. What is the length? It goes from x sub k minus 1 to x sub k. We'll just call that length the change in x in the kth subinterval. Does that sound okay with you guys?
Yes.
Okay. And what about the width or the height of it? Well, the height of this rectangle is just whatever the function is at this x value, which would be f of c sub k, which, haha, yes, I know what that looks like, sort of. So funny. All right, so what is our area? It's just delta x sub k times f of c sub k. Would you all agree that that is a generic representation, if I multiply those together, of the area of any rectangle within here?
Yes.
So if k was 1, it'd be delta x sub 1 times f of c sub 1, right? And if k was 2, it'd be delta x sub 2 times f of c sub 2. And it's still a little bit of a problem because, you know, f of c sub 1 and f of c sub 2 and f of c sub 3 and so on are all different. And delta x sub 1 and delta x sub 2 and delta x sub 3 might also all be different because nothing in here says that each of these subintervals are equal to each other. And in fact, if you look at it, like it's pretty clear that some of them are not equal. Like they don't have the same width, right? That's okay. We'll be able to deal with that. So we feel okay about that? Everything I've talked about so far?
Yeah.
Okay. So this thing that we're now going to have, and this is my height or my width and my length here, within the summation, this thing is called a Riemann sum. And I don't think I've used that term before, but it's a Riemann sum for whatever function we have, f, on an interval from a to b. And as we talked about, as the lengths of those sum intervals get smaller and smaller and smaller, it's going to allow us to have a more accurate representation of that area. Good? Hopefully good. So, now, if we wanted to get more subintervals, we'd have to make our subintervals smaller. True? Because more subintervals means better approximation of the area. True? And that's what we want, is we want the best approximation of the area we can get. So let's make the largest subinterval become very, 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 very small. Let's make the largest subinterval go towards 0, get very close to 0. And if I shrink that subinterval down, let's say by cutting each of the subintervals in half, and then doing that again, and then again, and again, and again, until the kth subinterval, until the largest one that I have is very close to 0, what's happening to all the other ones is I do the same thing. They're also getting very, very small, aren't they? So if I go back here and think about this, if I split this first subinterval and the second subinterval and the third and the fourth and the kth and all of them up into 2 subintervals each, right? If I cut each of these in half, they'd be, well, I have twice as many, right? And they'd be smaller. And then if I did that again, it'd be even smaller. And if I did it again with all of them, it'd be even smaller. And the ones, let's say, in my largest subinterval, this one, because it looks like it's the largest, would still be bigger than all the rest of them, but they'd still be very, very small, wouldn't they? Are we following or no? Is anybody still out there?
Yeah, following.
Okay, so do we agree that if I were to shrink each of these subintervals down at the same rate by like splitting them into, split this one into 1,000,000 subintervals and this one into 1,000,000 and this one into 1,000,000 and all of them into 1,000,000, the largest one, when I split it into 1,000,000, those 1,000,000 would still be bigger than all the rest of them?
Yeah.
Just ever so slightly, and they'd all be very, very, very small? Okay. Well, the largest subinterval we give a special name to, we call it the norm of the partition. Okay, so the largest subinterval is called the norm of the partition, and we want to make that get as small as possible. We want to get it as close to 0 as we possibly could. And so the problem then would be, how do we make it equal 0 or get very, very close to 0 without it actually being 0? Because if I have that subinterval's length equal 0, that means that delta x sub k is 0. And if that's 0, I'm just summing together a bunch of zeros, which is 0. So how do I make something 0 without actually making it 0?
Take a limit.
Take a limit. So that's exactly what we're going to do. We're going to try to take a limit as the largest subinterval, the norm of the partition, approaches 0, of the summation from k equals 1 to n, so from the first subinterval to the nth subinterval, of the areas of each of those subintervals, which is f of c sub k times delta x sub k. And this right here would effectively give us the exact area underneath the curve. This would be the exact area underneath the curve. If we took the limit as the largest subinterval approached 0 of the sum from the first subinterval to the nth subinterval of the areas of all of them, of each of those rectangles, that would be the exact area underneath the curve. Okay. And we call this thing I, or the integral. Okay. This is called the integral of our function, and that is the representation of the exact area under the curve. Good or no?
So why can the intervals be different lengths now? Like before, when we were approximating it with rectangles, they're all the same.
Right, well, they didn't have to be. I think I gave you a couple maybe where they weren't the same on the chart, maybe with a chart, maybe I didn't. But they they can, however we decide to divide it up, sometimes they're the same and sometimes they're not the same. Generally, we would like them to be the same, but there's no guarantee that they always will be the same. So that's why we have to do it, assuming that they're not the same. And what we're going to do is we're going to generalize this equation that we've written here, this expression that we've written here, for when they are the same length. And it's going to actually make things a lot simpler, because if we look at this, this is pretty dang complicated, right? It's got one variable, it's got two variables, I missed this one, three variables, four variables, five different variables. True? It's got five different variables. It's got a delta, so it's got, and a sigma, two different Greek letters. It's got a summation, it's got a limit, and it's got a function involved in it. It's got a whole heck of a lot of different things going on in it. And that is because the subintervals aren't necessarily of equal length. But when we generalize this for equal subintervals, which we can effectively always do, it makes it a much easier equation. Does that answer your question, or did I just make it more complicated?
No, I think I get it.
Okay. So what we're going to do then is we're going to say, instead of having all of these differently sized subintervals, we're going to generalize that into equal subintervals. And if they're all equal, there's not a largest one. There's no norm of the partition to approach zero. All we want is we want the number of the subintervals to approach what?
Infinity.
Infinity. We want to have an infinite number of subintervals. So if we make the subintervals equal, we can convert this into a limit as n approaches infinity. So as the number of subintervals approaches infinity, of the sum from the first to the end of the areas, which at least gets rid of that norm of the partition joke. And if each of the subintervals is equal, the delta x sub k no longer has to be delta x sub k. It can just be delta x, because each of those subintervals has the same length. In fact, they have a length of delta x over b minus, or sorry, delta x is equal to b minus a over n, where b minus a is the length of the entire interval divided by n, the number of subintervals. And so this right here is what we call a definite integral of our function. And a definite integral of a function is what gives us the area underneath the curve. And so effectively what this means, I know if we read it out, it says the limit as n approaches infinity of the sum from k equals 1 to n of f of c sub k times delta x. Well, what this is the limit as the number of subintervals approaches infinity of the sum of the areas of all the rectangles. Right? These are still the areas of the rectangles. We're summing them from the first one to the last one, and we're letting n go towards infinity. So we're summing together an infinite number of little rectangles underneath this curve. A very narrow, infinitesimally thin rectangles. Does that make sense to everybody or no? Or does anybody have any questions? No questions?
So is this just like a rewritten like version of the equation with the norm?
Yes, it's saying instead of, so here, this is the subintervals are not necessarily the same, right? So we have to have a largest one and each one has a different length. But now if they each have the same length, then delta x sub k is just delta x. And we no longer have to make the biggest one approach zero. We can just make the number of them approach infinity. Does that make sense?
Yeah, so like which one of them will we be using like more often?
This one.
Okay.
This is the simplified version. And in fact, for the next day or two, we're going to use this one, but then we're going to learn some rules so that we don't have to do the limit and the summation every time. But this is effectively what an integral is doing. So we're going to learn how to just integrate a function really easily and come up with a value. It's important that you guys understand what's happening and how we find that actual value, not just that we can figure out, oh, you know, I can use these rules that I'm going to give you a bunch of rules and you can just use them to find the area. But for a lot of things that happen in higher calculus classes and higher math classes, it's really important to understand this is what we're doing, is we're summing together all these little tiny thin rectangles to come up with the full area under the curve. And this is what's happening behind the scenes when you use all the formulas that I'm going to give you eventually. Does that help or no?
Yeah.
Okay, cool. All right, so this is what we're going to use. Hopefully it all sort of makes sense. This is our number of subintervals approaching infinity. This is the sum of all the areas of the rectangles. And so this limit can be equated to this other notation that I was using earlier today, just a little bit, where I was just saying this means the area under the curve. Well, that's exactly what it means. It means the area under the curve from A to B. And it is equivalent to this limit and summation that we were just talking about. And this right here is the notation that we will use 99% of the time, right? More than 99% of the time. After the next day or two, we will always use this notation. You need to know this one so you understand what's happening, and also because you will have to do a thing or two with it on the AP test. But 99% of what we do will be with this notation. So this notation with this little squiggly s, which is called an integral sign, this is Leibniz's notation. This notation was originally done by Newton, right? So both Newton and Leibniz were both developing calculus sort of at the same time, working together and not together on it, sort of. And Newton wrote out everything in this notation, and Leibniz was like, well, it'd be so much simpler if we came up with some rules and did it like this. And so that's what happened. And so when we talk about an integral, when I talk about an integral from now on, this is what I'm talking about, is this squiggly s. It's an integral sign. So it means the area under the curve from A to B of a function dx. And this dx, if you remember back to when we were doing differentials with our derivatives, we had a dx. And what did that dx represent? Some of you just resubmitted the
A small change in x.
A small change in x, right? That just represents a small change in x. And that's exactly what it is here. It's an infinitesimally, yes, hopefully I spell this right, infinitesimally small change in x. And that's exactly what this delta x is, right? This delta x is a very tiny change in the x. It's the length, the width, let's say we'll call it the width, right? It's the change in the x value of each rectangle when there are an infinite number of rectangles. It's effectively 0, except that it can't be 0, right? And so that's what this dx is. It equates to the delta x here, and the f of x here, I want that to be a different color, the f of x here equates to our function f of c sub k, where we're evaluating the function at the midpoint. Or we could do it at a right endpoint or a left endpoint, it doesn't matter. And then the integral sign equates to this limit of the summation. Good or no? And so we call the lower value here, the a value, the lower limit, the b value, the upper limit. Those are just the restrictions on where we're looking for the area. The integral sign tells us that's what we're looking for, is the area underneath this curve, and then our integrand is everything inside the integral sign. Good or no?
Good.
Cool. So the last thing we're going to do, and we have like 1 minute here, and we have plenty of time to do this, is we're going to take a function that is in Newton's notation, with a little bit of extra information here at the beginning and rewrite it into a Leibniz notation using an integral sign rather than using the limit and the summation. So what we want to know is, or what we're going to do is we're going to take an interval from -1 to 3 and partition it out into n subintervals of equal length. M sub k is the midpoint of the kth subinterval, so that's what these are. And we want this limit to be expressed as an integral. So we know we're going to have an integral sign. And where are we looking for the area of this function?
From -1 to 3.
From -1 to 3, so that's my lower limit and my upper limit. And the height of each of the rectangles should be found from this. Right, my function is just a direct result of this. 3x squared minus 2x plus 5. And my delta x equates to the dx. And so this integral could be expressed as this limit, or this limit could be expressed as this integral. And these are equivalent based on this interval that we were given. If I said the interval from -1 to 4, the only thing that would change would be -1 to 4. Does that make sense? Cool. That's it. We're done for the day. Hooray. Any questions?